Hi, welcome to lesson 16, linear programs and canonical forms. So we're going to start this by talking about some linear algebra. I just want to remind you, why are we doing this? We're doing this because, remember, from lesson 15, we need to convert linear programs into an equivalent LP with at least one extreme point. And we have seen that you can have LPs without extreme points. The other reason why we want to do canonical form, which is going to be the form we're going to convert it into. So that's reason one. The other reason is that we want a more systematic LP form. Okay, because right now, we have the ability to have like greater or equal to, less than or equal to, equality constraints. It's too much for us to have a systematic way to look at it. I mean, you could look at it this way, but it'd be very complicated. And instead, we're going to go to a form which really has a very nice form. Okay, so this is also sometimes called standard form in other textbooks. And I believe the second edition of this textbook is going to switch it to standard form. Anyway, we're going to start with some linear algebra. So some linear algebra, we have to compute a matrix vector product. So this is just review of linear algebra. Recall that AX, so A is this matrix here, X is the matrix here, AX, which is, of course, 1, 5, 9, 2, 8, 3, times X1, X2, X3. You can think of it in a couple ways. One way I like to think about it is basically these are weights on the columns of A. Okay, so this is actually equal to the column vector 1, 5 times x1 plus the column vector 9, 2 times x2 plus the column vector 8, 3 times x3. And of course, the other way of writing it, which is equivalent, is this is a two-dimensional vector where the first component is x1 plus 9x2 plus 8x3. And the second component is 5x1 plus 2x2 plus 3x3. Okay, so you should try it yourself with the following. And of course, this is going to be part of the assessment for this lecture. Okay. I'm going to just go to the end of this page and talk about what our canonical form is going to be like, and then I'm going to stop the video and let you think about it. Basically, we're going to be able to write all linear programs in the following way. And they're going to be equivalent to the original one, possibly with more variables and possibly with more constraints. But not too many more. That's the whole trick. So it turns out that all LPs can be written as follows. You can see the objective is not any different, but all equality constraints for the complicated constraints. And by that, I mean the only not complicated constraints are these ones. So it's over non-negative variables. Okay. So this is going to be the form where our simplex works on. And you should think about how what this form is going to mean. If you think of, and it's going to have direct impacts on our ability to simplify how we think about basic feasible solutions, simplify how we think about feasible directions, and is going to drive our ability to really make simplex a lot easier to write down. And that's what we'll use. Okay, so we can also write this in what's called vector matrix formation, and it takes this so you can see we've gone from sort of a complicated less than or equal to, greater or equal to, equal constraints, possibly non-negative variables, possibly non-positive variables, possibly free variables. We've written them in this nicer form. And then using vector notation and matrix notation, we can even write it in a simpler way. We can write all linear programs so they look like this: C transpose X subject to AX equals B, X non-negative, okay? And you should just keep in mind that this is a dot product. Okay, so now we have to be careful about what everything is. This is a dot product. This is a matrix vector product here at AX. B is a vector. So this is saying that AX equals B is a vector equality, and basically it represents M equality constraints. This is N inequality constraints, right? N non-negativity constraints. Okay. So when we go to problem 2, and I'm going to stop after this before we go on and let you do the assessment yourself. If we look at this, basically, if we let the vector x equal, and I'll put a little hat over x just to indicate it's different than the x there, that'll be x, y, and z. Okay. The c vector here would be equal to 3, 4, and -1. B will equal 10, 5. And the A matrix equals 2, 7, -3, 2, 1, -8. And then the problem is you can see it's in canonical form. It has the same properties as before. And so we can just write it succinctly as max C transpose X. And I'll put the little hat on the X so we know that it's this X, subject to AX hat equals B, X non-negative. So convince yourself these are the same. And I'm going to stop here, and you can look at the assessment questions associated with this problem.